Hello everyone, we are continuing with our lecture series on design of structural steel connections in our YouTube channel. And in our previous two classes, first we looked at the design of a beam column shear connection manually, and we looked at the same design through an Excel sheet in our previous lecture. Today we will try to model the connection in IDEA StatiCa and then try to design for that connection. So I have opened IDEA StatiCa here. So let me click on this connection and open our connection page here. It may take some time. So what we did in our previous lectures was that we designed a beam column shear connection in which both the beam and the column were I section. So what we did is we took two I sections, both beam and column, and we designed a shear connection. So we will do the same in IDEA StatiCa today. If you are familiar with the interface of IDEA StatiCa, then you may be familiar with this beginning page also. You can see here different modules are given for you for easy modeling of your connection. First, there is class in which you may want to design a beam column connection or a beam to beam connection, or you may wish to design for this type of connection, which is particularly seen in truss members when you want to connect the inclined and horizontal members. Then there is a class for base plate connections also, and then many other types of connection. So what we would like to do is you can also begin with a blank connection. That means if you want to define your beam and column members by yourself, if you do not want to select any type of class or geometry here, then you may also begin with a blank section. So what I will do is I will choose this beam column connection, and for beam column connection also there are different geometries given here. And if you have watched our previous lectures, then there you can see that what we have done is we have connected our beam member to the flanges of our column. So I'm going to select this second type here. You can see that the beam is connected to the flange of the column section. And for this design here in the third column, what I will do is I will choose a blank connection here, and then I will start modeling by myself. And you can also choose certain parameters here. You can change these parameters later when you are modeling also. So I'm not going to do anything here. The only thing I want to make sure is the design code selected here is Indian code. So different codes are available here. Make sure that the Indian code is selected, and then click on create project. So after clicking on create project, IDEA StatiCa will take you to this page here. So if you remember, what was the structural steel section that we used as beam and column? So let me just write here. For beam, we considered an I section with flanges size of 150 by 10 and the wave section 350 by 6. And for column, we chose an I section with flange size same as that of beam, 150 by 10, and wave section 450 by 8. So just remember this here. Now what you see on your screen is first this is the, before going into the modeling part of our connection here, let us just talk a little bit about IDEA StatiCa. This is the interface of IDEA StatiCa, and you can see different tabs here: project, design, check, report, materials. Whenever currently this design tab is active, and whenever we are modeling our member sections, then we will be working in this design tab. We will also apply load under this design tab here, and finally after the analysis of our section, we will go to this check tab and see various results there. And also there is a tab for report where you can generate detailed report which contains all the things that we have done on this software, including your modeling, the analysis results, and the design results also. So one thing about IDEA StatiCa is IDEA StatiCa in itself is not a design software. That means suppose if you have a design moment of 150 kilonewton meter and a shear force of suppose 50 kilonewton, then IDEA StatiCa doesn't give you a definite connection when you give these design action values. That means you cannot say to IDEA StatiCa that I have to design a shear connection, not a shear connection in this case. You cannot say to IDEA StatiCa that I have to design a moment connection where the connection have to resist a moment of 150 kilonewton meter and a shear force of 50 kilonewton. Saying that does not give the results in IDEA StatiCa. What you have to do is you have to model your connection and then you have to apply the loads and then you have to check for the results. You have to check if the results are within the safe limit, and if the results are not within the safe limit, then you have to make changes in your model by yourself. So in itself, IDEA StatiCa is not a design software. Rather, you model your connections there and you check for the model based on the loads that are acting on your connection. So IDEA StatiCa is capable of performing various types of analysis. This IDEA StatiCa version that I am using currently is the educational version. So if I see here, there should be some options shown in this section here. Okay, no, these options are not shown here. Maybe because I am using an educational version, but you have to remember that IDEA StatiCa is capable of performing various types of analysis. So the type of analysis that we will be using mostly to model our connection and to check for the results is what IDEA StatiCa calls EPS, and this is elastic plastic stress strain analysis. So this is the normal analysis technique that we will be using to model our connections and check for the results. So IDEA StatiCa is also capable of performing stiffness based analysis, or ST, stiffness based analysis. So this type of analysis is used to check whether a connection that you have modeled is capable of resisting moments or not. That means for classification of our connections based on its stiffness, whether it is a shear connection or a moment connection, this stiffness based analysis is used. And there are also other options such as this capacity design approach, and we have this design resistance calculation of any particular joint, DR analysis, and finally fatigue analysis, FAT. So these 4 or 5 types of analysis, IDEA StatiCa is capable of performing these 4 or 5 types of analysis. Now currently we are in this EPS analysis, elastic plastic stress strain analysis, to model and check for our connection. So after knowing this much about IDEA StatiCa, now let us go into modeling of our connection. So we are under this design tab here. So let me write it again. Our beam section has flange of 150/10 and wave of 350/6, and our column section has a flange of 150/10 and wave of 450/8. Now to do that, let's see here. If you see in this part of the screen, you can see that first there are members here, and currently our members are C and B. C means column and B means beam. So if you click on this C, this column is highlighted here in brown color, and if you click on this B, the beam will be highlighted. And correspondingly, you can change the properties of C by clicking on C here, and on this right hand side, if you see here, you can change the properties including the cross section and different placement of your beam and column here. Similarly, you can do the same for beam also. And then you have the second option here, load effects, and if you click on this LE1, you can see that currently no load is applied here. All the load values for moment, shear forces and axial forces are 0. So you can apply load by going on to this option here, load effects. And operations means various capabilities of IDEA StatiCa that you can perform when modeling your connection. So the details of operation can also be found here. If you look at this last option here under design tab, you have the new operation option, and if you click on this, various operations you can perform in IDEA StatiCa. For example, you can cut any member, you can weld any member, you can use these batten plates, you can use these cleat plates, you can use these fin plates. So these operations, whenever you want to perform any new operation, then you can go to this operation option here. So first, what I will do is, let me use these sections that we have used in our manual calculations. So first I will change the column section here. And remember, these sections that we are using now, these are not standard sections. These are the welded or composed sections. Welded or composed sections. That means you have welded these plates to perform or to form our beam and columns. You have welded these plates in this way or in any other way. So these are not standard sections, rather these are welded or composed sections. You can also use standard sections, but since I have used these dimensions without considering any standard section, I will choose welded or composed section to define these member sections here. Okay, to do that, let me first click on this column here, and you can see that currently it is using our channel section of 200 mm. You can see here under this properties and cross section, it is using our Indian standard channel section of 200. So to change this, I will click on this edit parameters here. So if you click on this edit parameters, what you can do is, you can give a name to your connection here, or you can give a name to your member here. For example, you can say that it is a column. You can choose the geometry here by clicking on these dots here. You can choose various standard geometries. So you may use SB sections or JV sections or channel sections or medium beam sections. So by clicking on this, you can choose any standard cross section. And the material, that is the grade of steel, you may choose here. If you want to add other grades, you can click on this plus sign and add other grades also. So what was the grade of steel that we were using? Let me check on our Excel sheet. The grade of steel we were using was a yield stress of 350 Newton per mm square and an ultimate stress of 490 Newton per mm square. So let us, okay, it is already E350 is selected here, so this is okay. So now to select any welded or composed sections, what I have to do is I have to click on this plus sign here. And if you want to use standard rolled sections, then you may choose any rolled section under this tab here, rolled. But if you want to use welded or composed sections, you can click on this welded and composed section. Now we are using an I-beam, so under this welded and composed section, I will click on this I section here. Now I will give the name here. Okay, the name I will want to give is column. So what will be the height? So our column, if you see here, our column wave has a dimension of 450 over 8 and the flange section has a dimension of 150 over 10. So what will be our total depth of our section here? This will be the depth of our wave, 450 plus 2 times the thickness of our flange section, that is 2 times this 10 mm. So what depth do we get here? We get a depth of 470 mm. So I will write 470 here. Now for the flange parameters, the thickness that we are using for flange is 10 mm and the width of our flange is 150 mm. After that, the thickness of our wave that we are using is 8 mm here. Now after giving these dimensions, if you look at the diagram of your section here, you can see that the total depth of our section including the thickness of our flanges is 470 mm. The depth of our wave is 450 mm. The width of our flange is 150 mm and the thickness of our wave is 8 mm here. So this is the column that we will be using. The material will be 350 grade steel. Now this weld option that is here, this weld option has been included in the latest version of IDEA StatiCa. So since this is our welded or composed sections, that means we are using plate sections and we are welding them together to form our I section here. These weld sections, you have to give the parameters, or you have to give the size of the weld that is being used to connect these 3 different plates to compose our I section. So currently, if you can see here, the type of weld section that is being selected is a full penetration butt weld here. If you are using fillet weld, you can choose different options here, the fillet weld on one side or fillet weld on both sides. That means fillet weld may be done on one side only, or fillet weld may be done on both sides also. So when IDEA StatiCa checks your model, the size of this weld is also checked, whether based on the forces that is coming on your structure, these welds are sufficient or not. So currently we are not interested in checking this connection or checking this weld size here. What we are assuming is the weld size that is used to form this I section here, these are sufficient. So I'm not going into detail in this part here, but you can also check for this part, and this is a new feature that is added in the latest version of IDEA StatiCa. So after giving these parameters, I will click on OK. Okay, now you can see that this column is changed here. So before doing any other thing to this column, I will also change the size of beam here. So I will click on this beam here. I'll do the same thing here. Click on add new, go to welded composed sections and check this I section column. So rename this as beam. Now the total depth of the beam will be, the total depth of the beam will be 350 plus 2 times the thickness of flange here, tail. So this will be 370 mm. So let's input that parameter here. Height will be 370 mm. The thickness of our flange is again 10 mm. The width of our flange is 150 mm. And the thickness of our wave is 6 mm. The material or steel grade will be E350. And again this welds, I am not doing anything here. So this will be our beam section. Let's click on OK. So before proceeding any further, I will save this model. I will click Ctrl yes. So this Ctrl yes option does not work here. So let me just click on this save. I will give this name as beam column shear connection, save here. So now after saving this model, if you look at this diagram here, what you can see is, you can see a certain red plate here. So what this red plate is doing is, it is telling IDEA StatiCa that our column is our bearing member. That means whatever load we are applying on our beam, whether it is moment or any shear force, these loads will be borne by our column. That means our column will be resisting the loads, whatever loads that is coming onto our beam. So we are not concerned with the deformation of this column or beam here. This column section is only bearing the loads. What we are assuming when modeling our connection is the size of our column and the size of our beam are sufficient based on the frame structure or based on the structure that we are going to design. We are only concerned with the connection here. So our column will be assigned as bearing member. So this red plate that you can see at the bottom, this is telling us that column is our bearing member. If you click on this column here, see, you can see that the geometrical type here written is continuous. Now if you select this ended option, you can see the change that will happen here. So we want this column member is continuous, so I will select this continuous here. Now one thing that you can see here is that our beam is penetrating into the column member. If you see this part here, so this is not the real life situation, or this is not how we will be constructing our frame structure. In practically we are not going to do this. What we want to do is, if this is our column here, then our beam member will end somewhere here with very little spacing between this beam and column, and then we will be making some connections here. So to do that, we have to offset this beam member here. That means we have to shift the beam from this edge to this edge here. So to do that, what we will do is, let's see first how much we have to offset it. Currently this end of the beam member, this is connecting, or this is in line with the center of our column section here. Now we have to offset this by certain distance. So how much we have to offset? Let's see here. So what is the total depth of our wave section here? The total depth of our column wave is 450 mm. So if we divide it by 2, 450 by 2 will be 225 mm. And we have to add this thickness of our flange section also. The thickness of our flange is 10 mm. So 225 plus 10 is 235 mm. Now let's see what happens if we shift this by 235 mm. So to shift the beam, this beam option is already selected here. Before shifting the beam, let me activate this option of local coordinate system. This local coordinate system currently is not visible, I guess. Okay, this local coordinate system is not visible. So if it is not visible, then let us check in which direction can we offset here. So this we have, after selecting this beam option here, we have this position option, and in this position option we can shift either in X direction or Y direction or Z direction. So let us first shift in X direction by 235 mm and let us check if this will be okay. Okay, our first trial was correct here. This option, now this beam has been shifted. Since we are offsetting it by a positive 235 mm, now this beam seems to be offset in the right direction, in the direction that we want here. So if you look at the front view of this section, you can change the view by changing the cube here. If you look at the front view of this section, now you can see that this has exactly shifted, and now the edge of the column and the beam are currently just touching each other. So now what we want to do is, we may not want to exactly touch this, because we will also be using some cleat sections for connecting this beam and column here. So what I will do is, I will offset it by an extra 5 or 10 mm. So let's just say that we are currently using 5 mm. So total offset will be 240 mm. Now you can see a certain gap here. Now let's say that this is the offset that we want. So finally, if you want to change the inclination of your beam or column member, then you can change the angle, this beta, gamma and alpha angle also. Currently we are not interested with that. And finally our this column and beam has been modeled here. So this column has been modeled here and the beam also have been modeled here. Now what we want to do is, now we want to add some cleat member that we have seen in our previous two lectures, which are used to connect this beam and column member. And then we will also want to add the bolts and the weld that will be used to connect the cleat member to our beam and column. Now cleat member will be a new operation, whether it is a cleat member, any end plate or any welding or cutting section or bolting section, that will be defined by operation here. Now you can either add a new operation by right clicking on this operation and clicking on new operation, or you can also go to your design tab and click on this operation here. So I will just right click on this operations and then select new operation. Now see here, where is the cleat member that you want to use here. If you look at these diagrams, then you have a base plate here, then you have these splice sections for both beam and column, then you have these stiffeners here, or what IDEA StatiCa calls widener. Now if you see, this is the cleat section, the name is also cleat here. This is the cleat section that we want to use as a new operation. So this, click on this cleat, and now then you have to choose for this cleat member what is the bolt assembly, the grade of your bolt and the diameter of your bolt. So if I go back to my Excel sheet, currently what we have already done is we have already manually calculated or manually designed the section here. So to just see how IDEA StatiCa works, I am using the same parameters. Otherwise, if you are directly designing your connection using this IDEA StatiCa, then you may perform different trial and error. For now, what I will do is I will use the same parameters that we have adopted during our manual design. So if you look at the bolt details, we have used grade 8.8 bolts and 16 mm diameter bolts. So just select the grade here 8.8 and the diameter will be M16 and then click on OK. So now after clicking on OK, this cleat is added here, and you can see that the cleat diagram or the cleat has also been modeled here. So you can also rotate the view and see that that cleat has been added to both sides here. So currently what is happening is the cleat is being bolted to the beam also and column also, but that was not what we used in our manual calculations. What we did was the cleat was being bolted to our beam wave, whereas it was being welded to our column flange here. So what we have to do is we have to change this. So now that the cleat operation has been added, you can also click on cleat and you can see the different parameters on this right hand side here. If you want to change any parameters related to the cleat, you have to work in this right hand side here. Okay, let's go into the details of some of these parameters. First, the member here that is being selected is B wave 1. So before going into detail of this, what you can see is the system or the principle that IDEA StatiCa uses is CVFEM. If you have read IDEA StatiCa manual, then you can find there also, that is component based finite element method. So what IDEA StatiCa has done here is it has divided our beam and column section and also our cleat bolts into different members or different components. So if you click on the wave section, if you click on this fan section of your column, or just don't click it, if you just keep your mouse cursor on the top of this column flange, and if you look at the name here below, what it says is this has been named as C top flange 1. Similarly, if you put your mouse cursor on the wave of your column, you can see the name is C wave 1. C wave 1. Similarly, this is C bottom flange 1. And similarly, you can check for beam also. If you put your mouse cursor here, then you can see this is named as B wave 1, this is B top flange 1, and the bottom component is B, bottom flange 1. So now let's go to this Cleat operation, and you can see that the member here is B wave 1, which is our B wave 1. So this is the B wave 1. That means the Cleat is connected to this B wave 1, and the member 2 need not be specified. What happens if you use this as C? Okay, you can see that there will be some error. You can check what these different options does by trying yourself also. So you can see that member 2 will be not specified, but rather this connected to member will be column. So the Cleat is connected to the wave of our beam B wave 1 and our column here. And the Cleat profile that is currently being used is a Indian standard angle section of 80 by 80, and the thickness of the angle section is 8 here. And there is another option of this location here, both. So what happens if you choose this front option here? You choose this front option and then you rotate this option here. You can see that there is no Cleat at the back side. Similarly, if you choose the location as rear, the Cleat will only be connected to the back side, and there is no Cleat over the front side. We want the Cleat on both of our sides, so the location will be both here. Now the connection type currently is bolted here, but we do not want it bolted to both beam and column. We want it bolted to our beam and then welded to our column. So we have 4 options here. Let us see here. If you see the option here, this bolted option, what this bolted option does is it bolts our Cleat to both column and welded member. This welded option, if you click on this welded option, now you can see that the Cleat plate is welded to both of our column and beam member here. Select this bolted to connected to member. So which is the connected to member here? If you see this option here, connected to member, our connected to member is our column here. So if you select the option bolted to connected member, what it will do is the Cleat will be bolted to our column, since our connected to member is our column, and then this will be welded to our beam. Again, this is not the option that we were using. So finally, go to this connection type again and select this bolted to member. Now our member is B wave 1. You can see here at the very top, our member is the wave 1 of our beam. Now what will be done is our Cleat will be bolted to our beam and then welded to our column. And then there are different options for Cleat length, Cleat shift and dimensions. So we will come to this again. Now let us see what is happening is, if you look at your model here, there are 4 number of bolts currently, and then the welding is done on 2 sides here. The welding that is connecting our Cleat to our column section, this welding is being performed at the very top and at the down. So what we did during our manual calculation was that we considered welding only along the length of our Cleat here. So we assume that there is no welding at the very top. So we have to change the parameters to make this, and also we used 2 bolts here, 1 bolt here and 1 bolt here in a single line when we are designing manually. So we have to change the number and location of our bolts also. So to do that, let me again click on this Cleat 1 option here. So for currently welding, what is happening is you can either weld on this side. If you choose this fillet weld front side, then welding is being performed there. If you choose this fillet weld back side, you can see that this welding, the triangle shape of our weld changes. It changes from this to this. So of course this is not the type of welding that will be performed in our field. You can also choose this on front and back also. Again, this is not the type of welding that will be performed in field. Practically this is not possible. You can also check for, or you can also select full penetration butt weld, such that now there are no, you can see that the butt weld is being performed at the back and there are no fillet weld here. So if you look at this option here, then there is no option to manually model the weld that we are using during our manual design. So what we will do is, currently in this option of Cleat option here, what we will do is, first we will suppose that there is no weld here, and then we will add a weld by ourselves. So check this no weld option here. Now there is no weld here. So now if we are selecting no weld here, how can we add a weld here manually? To do that, again we have to go to this operation option, operation tab at the very top. Now if you click on this operation tab, now select or now search for our weld option here, where this weld option has been given. So first we have cut this stiffener, widener, rib, then we can also open a notch or make an opening. Then we have end plate, stiffened end plate, stub, plate to plate, splice section. So there are different options available here. Now if you select this option here, you can see here this welder contact option is available here. So we will use this operation option to weld our cleat member to our column. So select this weld or contact option. Now you can see a new operation has been added here. Similarly, now you can make changes to this weld option to do our welding here. So before going into this weld option, we will make some changes here later. Let us make adjustments to the size of our cleat member and also the number and location of our bolts. Now to change for size of our cleat member, I am selecting this Cleat option again here. So what was the profile of our cleat, or what was the section of our cleat that we were using? Let me go back to this Excel sheet. So the thickness of the cleat that we were using was a thickness of 5 mm. So what was the length of the cleat? The required length of the cleat came out to be 160 mm, and we assumed the width of cleat to be 75 mm. So since this the profile of our width determines the width of our cleat, you can select this 75 mm angle section here. But be aware that we did not take into account this, or we forgot this when we were using manual calculation. So what happens is, if you select a profile of your cleat is, suppose we are using an angle section of 75/75. What this does is, currently what is the width of our column? The width of our flanges of our column we have taken is 150 mm. So what happens if we use an angle section of 75 mm? First, there is a certain thickness of beam, the beam that is being attached here. Okay, let me just draw this much, not this part. This wave of the beam that we are attaching here, or attaching to the flanges of our column, this has a certain thickness, and that thickness we are assuming is 6 mm. So if this thickness is 6 mm, what is the space available here? So this space available here will be our 150 mm minus 6 mm divided by 2. So this will be 144/2. That means 72 mm. So this IDEA 75/75 section cannot, if you use this profile of your cleat angle here, then this will come out of our column flange here. So we cannot use this IDEA 75/75. Can we use 70? Can we use angle of 70 mm? Yes, we can use angle of 70 mm, but again there may be, since we are welding on this side here, there may not be space available for welding here. So we will use a standard angle section of width less than 70 mm. So let me show you what I am trying to say here. Currently the profile of our cleat is IS 80/80 section, or square angle, or this is equal angle. Let's not say square, equal angle. So if you look at the front view of our, okay, let's just look at the side view. If you look at the side view and zoom here, what you can see is this cleat size, or this cleat dimension, is protruding out of our column flange. So this is not the modeling that we want to perform here. So let me just change this angle section here by clicking on this plus sign here. You can use either a welded or composed section and a rolled section also. Let me say that I am using a rolled section currently. I will select this angle section, and for geometry I will click on this 3 dots here and select a lesser size. That means currently we have 80 mm. Let me say that I am using a 75 mm angle section. Okay. Now you can see still it is protruding out, still it is bigger than the flange size. So I will change this again. Okay, I will use a 65 over 65 mm equal angle, 65 by 65, and the thickness will be 5 mm here. So let me choose this ISA 65 65 5, click on OK and click on OK. Okay, now it is sufficient. If you can see here, now we have space available for welding also. Okay, let me do this again. Now if you see here, we have space available on both sides for our welding. So this thing we did not take care when we were designing manually. When we are doing the same model in our IDEA StatiCa, then we came to know about it, we realized it, and we have selected a small width of our angle section. Okay, now we have chosen this as our angle section here that will use as cleat. So let me select this cleat again. Now this is the profile that we will be using. The cleat length here we have taken to be 160 mm. So let me write it 160 mm. Now you can see the cleat length has increased here. Now for bolts we have to make changes here at this last option here under bolts. So the grade of our bolt that we have already selected at the very beginning, M16 16 mm diameter 8.8 grade bolt. The spacing and the location of our bolts will be determined by these distances here, transverse and longitudinal. These distances will determine. So if you are unaware how to use these two options, first delete everything and write 0 and 0 here. Now if you insert 0 values for these both options, you can see that the bolt, there is a single bolt and it is at the very center of our cleat section. So 80 mm in the top side and at the bottom also 80 mm. So what happens if you increase the transverse distance to, let us say, 20 mm? Now you can see that two bolts have been modeled here and at a distance of 40 mm. So what this option transverse mm of 20 mm is doing is that if you say that this is the center line of your cleat here, so that this is also 80 mm, since our total length is 160 mm, this is also 80 mm and this is also 80 mm. So what this transverse option of 20 mm is doing is, this is placing two bolts in this line here at a distance of 20 mm from this center line. So this is also 20 mm and this is also 20 mm. So why this transverse distance of 20 mm is placing two bolts at a distance of 20 mm from center line? It's because if you look at this option here, if you look at this dimensions option here, we have selected the center line option. So what happens if you change these dimensions to top of steel? Now you can see that our bolt location has shifted here. Not only bolt location, our cleat location has also shifted. So for easiness, what we are choosing here is center line and this is our bolt option. What happens if you do the same to this longitudinal distance? If you insert 20 also here, two lines of bolt. So two lines of bolt, there is no two lines of bolt. What this is doing is, it is shifting our bolt location from this center of our bolt to our right hand edge. So we do not want this, we want it to be at the center. So let me change this back to 0. Now this transverse distance, what happened during our manual calculation, what we did is, so if you look at this our manual calculation here, what we have done is, okay, how many bolts did we use? Currently there are 3 bolts here. Okay, maybe we designed using 3 bolts, so total number of bolts required have been seen as 3 here. Okay, let's just use 3 bolts here. So how can we use 3 bolts here? What happens if I add another number here? Let me give a space and add 10 here. So you can see that now we have total 4 number of bolts. Okay, let me just start with 2 bolts here and see what will happen. We can check the analysis results and we can see what will happen. So now the distance between our 2 bolts is 40 mm. Let me change this to 50 mm. So to change this to 50 mm, I have to change this 20 to 25 here. So now the distance between these 2 bolts is 50 mm. And you can see that our end distances have also been changed to 55 mm and 55 mm here. So let me just use these 2 bolts currently. Now after determining the location of our bolts, let us apply weld here. So we applied a manual operation of weld by going into this operation tab here. Now this weld one, which 2 members or which 2 plates do we want to connect using this weld one? So this weld will be connecting our, if you hover over this Cleat plate here, this is named as Cleat 1A wave 1. If you look at the very bottom here, I'm just repeating, if you look at the very bottom here, you can see the name of that plate. So this weld should connect our Cleat 1 wave 1 to our this column bottom flange. So the first plate, let me write this as Cleat A wave 1, and the second plate will be column bottom flange 1. So now you can see that weld has been performed here. So when we are selecting these 2 plates here, the flange of our column and the Cleat plate here, why is the weld appearing on this side here? The weld may also have been on this top side, the weld may also have been on this bottom side. It is because the local edge index here has been selected as 1. What happens if we use this local index edge as 2? You can see that since our top edge is being named as 2 here, now the weld is performed on this side here. If you use this as 3, the weld you can see here is not present here, rather it has. So this edge is 3 here, so we do not want weld here, we want weld on this edge 1. So let me change this to 1. Now this is our weld. So what will be the size of this weld? The size of this weld you have to input here. So if you click on this 4 here, you can see that we are not giving the size of the weld here, rather we are giving the throat thickness here. So if you go back to our manual calculations, we are using a size of weld 4 mm, so the throat thickness came out to be 2.8 mm. So I will input this 2.8 here. Now you can see that the size of the weld has decreased here in diagram also. So this is the weld. So the weld has been applied to this cleat and to this column flange here. But if you look at your back cleat here, the weld option has to be applied here also. Weld has to be performed here also. So for this again you have to either add a new weld operation, or what we can do is I will just right click on this weld one and I will click on this copy. If I click on this copy, this weld 2 has been shown here. A new operation has been added. Now using this weld operation we are connecting this Cleat 1B wave 1. So let me select this option here, Cleat 1B wave 1. We are connecting this edge to our column flange. Since our second plate is already selected as column bottom flange and the local edge index is 1 here, this weld operation has been applied here. And since we copied weld 1, a throat thickness of 2.8 mm has also been applied here. So we need not change this again. Now after doing this, if you see here, our modeling operation is complete here. Is anything left? Our column is bearing member here. We have modeled our column also. We have modeled our beam. We have modeled our Cleat plates. And we have also drawn our bolts and our weld here. Now the second part is to apply our loads. So what will be our loads applied? Since this is our shear connection, we were only designing for a shear force of 150 kN in the downward direction. So I go to this load effects here and click on this LE1. Now this loads, since our column is a bearing member, we are not going to apply loads on our column. Rather, we are going to apply loads on our beam here. So we are going to apply our loads at the end of our beam. So N represents our axial force, Vy and Vz represents shear forces in two local member axes, that is Y and Z, and Mx, My and Mz are moment. Now this local coordinate system, okay, local coordinate system last time when we were shifting our beam was not visible. Now if you click on this LCS here, local coordinate system, then local coordinate system of our beam and our column members is visible now. Now you can see, if you see the coordinate system of a beam here, you can see that along the length of this beam we have X direction, along the height of this beam we have Z direction, and along the width of our flange plate we have the Y direction. So if we want to apply a shear force in the vertically downward direction, from this coordinate system you can see we have to apply our shear force in the negative Z direction. So I go to Vz here and apply here -150. Okay, now this load application has also been visible here. Just to rotate this member and see, our shear force is acting in the vertically downward direction. So this is the shear force for which we are going to design our connection here. So now the loads have also been applied. Let me just save this model. So for our today's lecture I am going to end here. We have completed the modeling part and we have also completed the load application part. In our next lecture we will look at the analysis results and the interpretation of our results. So till then, keep watching our YouTube channel and thank you.